This video is made possible because of Texas Instruments. Texas Instruments are pioneers of the semiconductor world. They make those tiny ICs which we see in the circuit board. Their team has provided the evaluation board of a boost converter which we are going to test and understand. This is the circuit of a boost converter. It works with the help of the magic of the inductor. If you know how a boost converter works and directly want to jump onto the design part, then please click on this timestamp. Well, a boost converter is made up of an input capacitor, inductor, switching elements such as active switch and passive switch, and an output capacitor. Active switch is nothing but a device like transistor whose switching can be controlled, and passive switch is a diode. We use a control circuit which regulates this output. We'll use the MOSFET transistor as an active switch and a Schottky diode in such applications because of their ability to switch at higher speed and handle higher power. We use a boost converter where we need the output voltage which is usually higher than the input voltage. It is a type of switching based DC to DC converter, and we are going to learn and design a constant voltage DC to DC converter, which means whatever happens, it will always supply constant voltage at the output. So to do that, this circuit has to work in harmony. Let's see the working of this boost converter. This is how this circuit would look like. This is our input source. Well, before going forward, one thing is very important to keep in mind. The inductor stores electromagnetic energy. It doesn't like change in current and it forces the current in the same direction. We will see the working of this converter in two parts. That is when the active switch is on and when it is off. The working of this circuit starts when this transistor switch turns on. At this time, the inductor starts charging and stores electromagnetic energy from the source. Why? Well, it's its job. The flow of the current is in this direction. As soon as this current is sufficiently charged, the switch is turned off. This is the second cycle of the operation. This time, the inductor releases this stored energy just like Ash's Pikachu gives Thunderbolt. Also, this inductor induces the flyback voltage, which has the value of L di by dt, where L is the value of the inductor and this is the change in current across the inductor with respect to time. This inductor releases this energy in the same direction, so its voltage polarity will be in the same direction. So this input voltage and flyback voltage add up and give us the boosted voltage. Because of this, the diode gets forward biased and provide the output to the load and charge up the output capacitor as well. This process of switching on and off of the MOSFET repeats continuously and we get constant output. When the MOSFET is on, the power is provided by this output capacitor to load. When it turns off, it is provided by this input voltage and inductor. Well, we want our output voltage to be stable, so we use a closed loop feedback system to control the MOSFET switching time, which checks the output voltage and guides this MOSFET about how much it should charge the inductor so that it gives optimum output voltage. This is how a boost converter works. Using this control mechanism, we get the constant voltage and constant current control. Now, we'll see how we can design such a boost converter. Instead of getting into complex control logic building, we have a better solution. We'll use an application specific IC like TPS55340 from Texas Instruments. It is very easy to design DC to DC converters using ASICs. All we need are some basic calculations, and in this case, we won't even need those. Trust me, it gets better. We select a few passive components, connect them to ASIC, and voila! We have designed our own boost DC to DC converter according to our requirements. But wait, there is more. These ASICs offer additional advantages like undervoltage protection, overcurrent protection, overvoltage protection, and over temperature protection. Even my health insurance doesn't give these many protections. Now, let's talk about this IC for a moment. This bad boy operates within the voltage range of 2.9 volts to 32 volts with a switching frequency of up to 1.2 megahertz. This switching frequency shows how fast this MOSFET switches from this DC to DC converter. It has an excellent efficiency and even comes with an internal MOSFET, eliminating the hassle of adding an external one. Plus, it can deliver up to 5 amperes output current. Now, we'll design a boost converter using this IC, where the input voltage ranges from 5 volts to 12 volts and we need output voltage of 24 volts constant, which requires 500 milliamperes current. So this is how the whole circuit will look like. Well, we have to do the calculation to select the components which are used in this circuit. It's not just like we use any components. But these calculations are a little complicated. So instead of doing this calculation on pen and paper, TI provided us an Excel sheet where we add all our desired values and this sheet does the calculation of the required component values. But if you still don't want to do that, then we can use TI's Webbench to directly design this circuit with very little effort. If you search this IC on TI's website and go all the way down, you can see this interface where we just have to give our design inputs such as input voltage, output voltage requirement, output current, and ambient temperature. And finally, click on design. Here it will show you the full circuit and components used in it, along with its part number and specifications. We don't need to do anything. We can even customize it more, like switching frequency and even changing the output voltage ripple, such things. We understood how to design this circuit and how it works. Now, let's say its actual version. There is no satisfaction of a design until and unless we test it in the real world. So as per the design, I already have an evaluation board of boost converter using TPS55340 from TI. This is the input side with the input capacitor. This small black is our IC. This is the boost inductor. This is the output diode and output capacitor section. Well, let's wire it up and test it out. I've connected the DC power supply input. Then I have connected an electronic load at the output side. This is basically a programmable resistive load which draws the current from the power supply. And this is our oscilloscope. I have connected oscilloscope to the switch node. Now I will turn on the power supply. Well, as you can see, the input voltage is 12 volts. And here on the electronic load, we can see the output voltage which is around 24 volts. Now I will turn on this electronic load which will draw around 500 milliamperes current. As you can see, it is drawing around 500 milliamperes and at the input it is drawing 1 ampere current. And here we can see the switch node. This is the waveform across the MOSFET. Now I will change the current drawing capacity of this load and still we can see the output voltage will remain constant. As you can see, it is driving around 300 milliamperes. Still the output voltage is constant, which is called as the load regulation. Now I will change the input voltage. We have designed our system which will work from 5 volts to 12 volts. Now I will reduce the voltage from 12 volts to 5 volts. Still the output voltage should remain constant. As I am reducing the input voltage, the output voltage stays constant, providing 500 milliamperes. And if you see the switching node, the duty cycle of the MOSFET switching is also changing. Here we have 5 volts input, still we are getting 24 volts output and 500 milliamperes current. This is called as line regulation. These boost converters are widely used in battery operated devices. solar power systems, LED drivers, and other applications who require higher output voltage than the input. And that's the wrap. I hope you picked up something useful from this video. The reference of this design is added in the description below. While checking the reference, don't forget to hit that subscribe button as well. It's right over there. I'll see you next time. Till then, stay hungry, stay foolish.